In this video, we will discuss cycle notation, a very useful way to represent permutations. Alright, so now we're going to introduce a new notation for permutations. First, let's go back to our visualization of my favorite permutation that we've been working with, or at least a permutation. It's worth pointing out that this approach of writing the set on the left and the set on the right works very, very well whenever you're working with a function whose domain and codomain are different. But when the codomain is the domain, there's another way to depict the function. Namely, you draw a graph like this. The vertices consists of the elements in the domain. And for each vertex, you draw an arrow leading from that vertex to its image under the function. And so you end up with this, what's called a directed graph. So you have these arrows. And the point is that for each vertex, there's exactly one arrow pointing away from the vertex. So it's a special type of directed graph. And this type of picture exists for any type of function whose domain and codomain are the same. But you start to see when you have bijections, you have this more interesting phenomenon. So 1 goes to 2, 2 goes to 4, 4 goes to 3, and 3 goes back to 1, and 5 goes to itself. So we see that we got this cycle going on here and this other cycle. And so you might ask yourself, is it the case when you have a bijection that you get the directed graph picture to look like this, a bunch of cycles? And that's one of the things we're going to get into. And the answer is yes. That when you have a bijection, you end up with a cycle decomposition. Now, to point out that you must have a bijection, it's worth pointing out what happens when you're not so lucky. So suppose instead this is our function, which is clearly not a bijection anymore. Well then 1 goes to 1, but 2 also goes to 1. 3 goes to 3, 4 goes to 4, and 5 goes to 2. So you no longer get this cycle decomposition, you get this funny path business too. And in general, for what's called an endo function, a function from a set to itself, when it's a finite set, you get weird graphs that look kind of like trees and cycles mixed together. So you really need a bijection to get this property. Going back to this example, again, it's much better to find a way to write the picture in some other notation so that we're not drawing edges all the time, which are sometimes hard to visualize. One way to denote this cycle decomposition is as follows. We write the elements on a cycle in clockwise order, following the directions of the arrows. So 1, 2, 3, 4, those are the vertices of the cycle when you follow the arrows. To indicate that this forms a cycle, we close this off with parentheses. Then the other cycle by itself gets its own set of parentheses. And so this is called the cycle notation. For a permutation, it looks like this in general. So the visual depiction here is that 1 goes to 3, which goes to 2, which goes back to 1. 7, 5, 8. 7 goes to 5, which goes to 8, which goes back to 7. And 9 goes to 4, goes to 6, goes back to 9. So there's a way to get the graph back from the cycle decomposition. And so, given one of these cycles, you write down the vertices in the order in which they appear as you go along the edges, and you close off with parentheses. And why do we use the parentheses? Because they inform the reader where one cycle ends and the next cycle begins. Of course, once you have cycle notation, how do you compute the function values? Well, what's sigma of 5? Well, 5 goes to 8, so sigma of 5 should be 8. How can I tell that from the cycle notation, though? Well, I locate which cycle 5 is in, and I look at the next value to the right. So sigma of 5 is 8. Similarly, sigma of 4 appears on this cycle. The next value on this cycle is 6. So sigma of 4 is 6. Finally, 2. 2 appears on this cycle. The next value on this cycle is not 7. It is 1, as you can see in the picture. So one important thing to always keep in mind is the element at the end of the cycle is being sent back to the beginning of the cycle. That's one thing that you have to get used to, unfortunately, with cycle notation. So that's one fact to know. And in fact, that tells you that in some sense, the order in a cycle is not entirely unique. Namely, that this cycle decomposition I just wrote down is actually the same permutation. All I did was take the 1 and move it to the back of that first cycle. But if you draw the graph here, it's still the same graph. It's still the same permutation. So a given cycle is the same if every time you remove the first element and put it at the back. Likewise, since these cycles are entirely disjoint, changing the order of the cycles among themselves does not change the permutation either. So that's another disadvantage. So one advantage of one-line notation is that the notation you get is always unique, whereas for cycle notation, the notation you get is not unique, unfortunately. However, it's worth pointing out this looping around is the only thing you're allowed to do. Why? Because this actually is different than if I switch the order of 1 and 2 here. That actually is a different permutation. Because if you write down the graph for that, the arrows change direction. So for instance here, sigma of 2 is 3, which is not what we had earlier. So order does matter on a cycle, with the exception that moving something from the front of a cycle to the back of the cycle doesn't change the permutation. But moving things, permuting things within a cycle does change the permutation, so you do have to be careful. Alright, that being said, you can also compute the inverse of an element. So what's sigma inverse of 5? Well, you find the cycle containing 5 and you look at the element to the left. It's 7. Why is that true? Because sigma of 7 is 5. As we discussed last time, sigma of I equals j if and only if I is equal to sigma inverse of j. So for cycle notation, you can easily compute inverses very quickly. In fact, the inverse can be found by just writing the cycles in reverse order, or the elements in each cycle in reverse order. So then the only real challenge is figuring out how to multiply two permutations written in cycle notation. Alright, now we're going to discuss how to multiply permutations in cycle notation. So suppose these are my two permutations, sigma and tau, and I want to multiply them together. And I want to get the result as a product of disjoint cycles. Well, what do I have to do? I have to figure out what the function does to 1, right? So now remember function composition. We recall sigma composed with tau of I is sigma of tau of I. So I need to figure out what tau of I is. So what is tau of 1? It is 2. So I get sigma of 2. What is sigma of 2? It is 4. So I see my permutation sends 1 to 4. And so now I'll start to show you what the shortcut method is. I want to see what my permutation does to 4. What do I do? My number right now is 4. And I start reading from right to left, looking at the cycles. And I ask myself, is 4 in this cycle? If it is, then this cycle sends 4 to the next element. So 4 appears here. Oops, sorry. And so 4 gets sent to 5. 5 doesn't appear on this cycle at all, so that permutation fixes the element 5. And so we see tau of 4 is 5. And now 5 doesn't appear on this cycle at all, and so 5 passes through that cycle unchanged. And now finally 5 appears on this cycle, and this cycle sends 5 to 1. And so 5 gets sent to 1. So one way to do this is to just keep looking at the numbers and asking yourself, reading from right to left, does this number appear on the cycle? If it does, what's the next number on the cycle? And then that's my new favorite number, and I forget my previous favorite number. And I keep doing this till I reach the end. And so now I see my new favorite number at the end is 1. 1 already appears in my answer, and so I can finish my cycle. My permutation sends 4 to 1. And so my answer is 1, 4 is a 2 cycle. Of course, I still need to figure out what happens to 2, 3, and 5. So let's see what happens to 2. So this first cycle doesn't have 2. So my favorite number is still 2. Now I look at the next cycle to the right. It does have 2. 2 is sent to 3. And so now my new favorite number is 3. So now my new favorite number is 3. I move to the left. 3 doesn't appear in this cycle, so my favorite number stays 3. I move to the left. 3 appears in this cycle. 3 is sent to 5. My new favorite number is 5. In general, when these permutations involve disjoint cycles like this, you're only going to change your value twice. Although if you look at homework problems in the textbook, oftentimes they'll be doing complicated products of multiple cycles, so it might change values more than twice. So we're here so far, and logic suggests only one of two things can happen. Either 5 gets sent to 3 or 5 gets sent to 2. Let's figure out which it is. My favorite number is 5. 5 appears in this cycle and is sent to 4. So my new favorite number is now 4. And then we see 4 is sent to 2. And so 5 is sent to 2 overall. And now logic dictates that 3 must be a fixed point. But you can check that. 3 is left alone. Then 3 gets sent to 1. Then 1 gets sent back to 3. So this is the product of these two permutations in cycle notation. Here's another example. And so one way is to do this approach, but I picked these examples because it's nice to learn some shortcuts. Namely, one shortcut you can learn is how to compute squares of a cycle directly. Remember, this is sigma of 1. So sigma of 2 is sigma of 1. And so the point I'm making is that sigma squared of 1 is found by just going over twice on the cycle. So we can replace this 4 cycle by saying 1, you're skip counting along the cycle twice. So instead of going over once, you go over twice. 1, 2. 1 goes to 5. Skip counting from the 5 by 2s, 5, 4, 1, going back, because whenever you reach the end of the cycle, you cycle back to the beginning. So skip counting from 5, you go 1, 2, 5 goes back to 1. And you get this 2 cycle. Similarly, starting from 2 and skip counting, 1, 2, 2 goes to 4. Skip counting from the 4, 4 goes to 1 goes to 2, 4 goes to 2. And so using this skip counting method allows you to compute powers of cycles directly without using this more complicated approach. And so like that, I've now simplified my calculation. And yes, as you can see, because this is a power of 2 and this was an even length cycle, it did break up into two cycles. All right, so now let's do the calculation of this product. What happens to 1? As I read from right to left, 1 doesn't appear in this cycle. 1 doesn't appear until you hit this cycle, so 1 goes to 5. Likewise, reading from right to left, 5 doesn't appear until that first 2 cycles, so 5 goes back to 1. Okay, that's not that interesting, but oh well. Likewise, 2. What does it do? In the first cycle, it goes to 4. My new favorite number is 4. On the next cycle over, it goes back to 2. And so 2 is a fixed point, or at 1 cycle. Similarly, 3. If you notice, 3 is missing completely, so that tells you 3 must be a 1 cycle. 4 goes to 6. And 6 never appears again, so 4 goes to 6. 6 goes to 8, 8 never appears again, so 6 goes to 8. 8 goes back to 2 on this first cycle, and then 2 goes to 4, so 8 goes to 4. And there's my answer. Worth noting, it is okay to drop 1 cycles from your answer sometimes, as long as it's clear what set you're working in. Finally, let's do this example. Here I have an inverse. So one way I think I've mentioned before is that the inverse is given by rewriting the elements in the opposite order. Please note I also sometimes alternate between writing the commas and not writing them, so I apologize if I ever drop the commas. It only matters when you have permutations with n at least 10, because then you actually need the commas. Alright, so let's try to figure out what happens. 1 goes to 4. 4 goes to 4, which goes to 2, which goes to 3. So 4 goes to 3. Note here I'm actually computing a product of 3 permutations. Alright, now 3 goes to 2, 2 goes to 3, 3 goes to 5, so 3 goes to 5. 5 goes to 3, 3 goes to 5, 5 goes to 2. Finally, 2 goes to 5, 5 goes to 1. And so there's our answer. And so looking ahead to a potential homework problem, it is worth noting how this answer changes from our original problem. The 2 became a 3, the 3 became a 5, and the 5 became a 2. The 2 became a 3, the 3 became a 5, and a 5 became a 2. So yes, it turns out this is a particular thing called conjugating a cycle, and there is this nice formula, shortcut, that you will learn.